In the last hour, India's Air Accident Investigation Bureau released its preliminary report. On June 13, one black box was found on a rooftop near the crash site, damaged but largely intact. Just 2 days later, the second was recovered from the debris, and both were flown to the AAIB lab. According to multiple credible sources, including Air Currents, Reuters, and the Wall Street Journal, the preliminary report revealed that switches controlling fuel flow to the jet's 2 engines were turned off. This led to an apparent loss of thrust shortly after takeoff. In this video, we'll analyze what happened, how it happened, and most importantly, why. The aircraft showed no signs of mechanical failure prior to the incident. None of the initial data suggests a fault in the engines, hydraulics, or any known components of the 787's complex flight systems. One of the challenging questions for investigators was how fast the ram air turbine, RAT, deployed. Normally, engine spin-down takes 30 to 60 seconds at altitude, but in this case, the RAT came out just 4 to 5 seconds after liftoff. Why so quickly? That device only deploys under 3 conditions on a Dreamliner: complete electrical failure, complete hydraulic failure, or a dual-engine failure. In this case, the RAT deployed almost immediately after takeoff, confirming that both fuel control switches, the very switches that regulate fuel flow to each engine, were found in the cutoff position. That's the equivalent of turning off the engine in your car while merging onto a highway. It instantly kills engine power. These switches are normally set to run before takeoff, and remain there throughout the flight. They're only moved to cut off after landing, once the aircraft is safely at the gate. Now, to put that in context, those fuel control switches are never meant to be touched in flight. They're switched on before departure, and only turned off after landing, once the aircraft is safely parked. But here's what makes this even more confusing. The 787's fuel switches are not casual toggles. They're physical levers that require a lift and pull action, purposely designed to avoid accidental contact. You can't just bump them or hit them by mistake. As Captain Steve, a senior airline pilot and aviation analyst, puts it, there's never been a case ever where both switches went to cut off by themselves. To flip them from run to cut off, a pilot must deliberately grasp 3 intentional steps, lift over a detent, and pull downward. So, was this human error? Or more importantly, how could both fuel switches have been mistakenly pulled to cut off at the same time by the pilots? Let's address the possibility. Is there ever a time where both fuel switches are moved to cut off mid-flight? Yes, but only during a specific procedure. In the event of a dual-engine failure at cruise altitude, the Boeing 787 checklist instructs both fuel control switches to be momentarily moved to cut off and then back to run to attempt a restart. But here's the critical point. There's no commercial aviation procedure where both switches are placed to cut off and left there, especially within seconds of takeoff. Normally, when one engine fails, the crew waits until 400 to 1,000 feet before running checklists. It's a methodical, highly choreographed process with multiple confirmations. So, could a pilot have made a mistake in panic, perhaps confusing engine shutdown procedure in the heat of the moment? Again, experts say that's not how training works. Pilots are drilled on engine-out scenarios repeatedly, and under no circumstances would a pilot touch a fuel lever before passing the engine-out altitude, typically 1,000 feet AGL, and certainly not both switches. On the other hand, the flight data recorder tells a different story, and it became the central mystery. The data shows they moved from run to cut off with a gap of just 1 second between them. That's not enough time for 2 deliberate human actions, and yet they were recorded as having been flipped individually. Could faulty software have signaled the wrong command? Could a short circuit or arc have mimicked human input? At this point, investigators aren't ruling anything out. They're also not calling it pilot error, at least not yet. However, the cockpit voice recorder adds another chilling layer. In the final seconds before the crash, one pilot is heard asking, "Why did you switch it to off?" To which the other responds, "I didn't switch it to off." This short exchange has become one of the most scrutinized pieces of evidence so far. Moments after the fuel cut, the recorders show that both engines attempted to restart. The switches were flipped back to run. One engine managed to spool back up, but only partially. The other fully reignited. This incomplete recovery left the Dreamliner with insufficient thrust. The aircraft, still heavy with fuel and low on altitude, could not sustain flight. And just seconds later, it plunged into the ground outside Ahmedabad. 241 lives were lost. Could the aircraft have recovered if things had gone differently? According to aviation safety investigator David Gleave, unlikely. Once the engines were starved of fuel, restarting them would have taken several seconds. And just like a car with a turbo trying to regain power at low speed, it's not immediate. There's a lag as the turbine spools back up. And in that narrow altitude window, seconds count. The 787 is designed to fly on one engine in case of an emergency. But not at takeoff altitude. And not with a full fuel load. And not when the engine only partially reignites. There simply wasn't enough time or power to recover. If both pilots believed the switches were still in the run position, was something else interfering? Could it be a design flaw? A software bug? Or worse, some unknown vulnerability in the 787's control systems? That's precisely what the FAA and NTSB are now working to uncover. At this point, investigators have no choice but to look closely at Boeing. Because if both pilots believe the switches were in the right position, and there's no sign of cockpit confusion, then the question becomes, did something inside the aircraft itself send the wrong signal? And that's where things get serious. While the fuel control systems themselves are manually operated and physically protected against accidental activation, they don't operate in isolation. They're connected to the 787's electronic engine control (EEC) system, software-driven computers that interpret pilot inputs and relay commands to the engines. And here's the concern. If there was a glitch, an electrical anomaly, or a corrupted data signal within that system, the engines may have received a cutoff command even if the pilots did nothing wrong. This isn't just speculation. It happened before. In the case of the 737 MAX, which involved the MCOS flight control system, exposed how internal cost-cutting and poor documentation led to the deployment of a system that could override pilot input, with devastating consequences. Many of those practices persisted into the Dreamliner program. Multiple engineers and analysts have since warned that Boeing's digital integration across its newer aircraft, particularly the 787, has become too opaque. Too many layers of automation, too many black box systems that pilots don't fully understand, and regulators can't easily audit. Unlike older aircraft, modern automation has reduced the need for hands-on flying, leaving many pilots less equipped to take control when critical systems fail. And now, with Flight 171, those concerns are back, front, and center. Because if a software process or corrupted signal can misinterpret the fuel switch's position and cut off power to both engines during takeoff, then the Dreamliner may not just have a pilot training problem. It may have a fundamental systems design flaw. The problem is, Boeing's recent track record makes it hard to give them the benefit of the doubt. Over the past few years, there have been repeated reports of production shortcuts, software inconsistencies, wiring defects, and a troubling tendency to keep problems quiet until forced to speak. In April 2024, whistleblower Sam Saliper testified before Congress, alleging that Boeing had improperly fastened critical components on Dreamliner fuselages, compressing carbon fiber layers and creating long-term fatigue risks. And his concerns weren't new. Boeing had previously admitted to gaps between the fuselage sections on hundreds of 787s, forcing inspections and delivery delays. Then, in early 2023, Boeing was forced to halt Dreamliner deliveries for several weeks due to another quality control lapse, incorrectly documented structural joints. Investigators are now digging into the architecture of the 787's fuel control logic, examining how physical switch positions are translated into digital commands, and whether any false logic paths could trigger an unintended shutdown. So far, Boeing has not issued any detailed public statements confirming whether a system-level malfunction, such as a misinterpreted fuel command or software logic fault. However, multiple sources confirm that regulators including the FAA and NTSB, along with Boeing's own engineering teams, are now reviewing the aircraft's electronic engine control architecture, associated wiring interfaces, and software logic chains, specifically the pathways that convert manual switch inputs into digital engine commands. The goal is to determine whether any failure, corruption, or conflict in these systems could have falsely triggered a fuel cutoff signal, even while the switches physically remain in the run position. Unfortunately, the full investigation could reportedly take up to 2 years to uncover what really went wrong. So, what do you think? Was this a rare isolated failure, or another chapter in a much bigger problem at Boeing? Let us know in the comments, and if you want to stay updated as more of this investigation unfolds, hit the subscribe and bell button. Until next time, I'm Mickey V. Have a great day.